Hey everybody, welcome back to Calculus 2. This will be lecture 8 of the course. And in this section, we're going to discuss inverse trig functions, and specifically integration involving antiderivatives that happen to be inverse trig functions. And we'll also discuss hyperbolic functions kind of briefly. But specifically, what kind of forms have antiderivatives that are hyperbolic functions. Many people will have not even heard of hyperbolic functions. It's not something that's commonly taught until you get into calculus, and even then it's sort of sparingly and frequently skipped. But we're going to touch on it briefly at the end, towards the end of this lecture. So let's go ahead and jump into it. And so we're going to call this section 1.8, and this will be inverse trig functions. And hyperbolic functions. Okay, so previously, we definitely talked about the derivatives of the inverse trig functions. We talked about all three of them, or I'm sorry, all six of them, but those six functions kind of fell into three pairs. So the derivatives of the inverse trig functions fall into three pairs. Okay, and so here's an example just to refresh your memory. The derivative of the arc sine we found was 1 over 1 minus x squared. Okay, so if you might recall that from Calculus 1. And we saw that the derivative of arc cosine was real similar in form, it just happened to be a negative. Okay, and and then what we saw is, as we go through if we were to go through the other four, in each case the derivative of one is the negative of the derivative of the other, right? So they always kind of have this nice symmetric sort of relationship. Okay, so given that we have talked about these inverse trig functions, basically they can be used as antiderivatives for integrals that have a particular form. And so that's what this first theorem is about. So we're going to let u be a differentiable function of x, and let a be greater than 0, like a real number, positive real number. Okay. Then we have the following. Okay, so 1 divided by a squared minus u squared. That integral is going to be the arc sine of u over a. Okay, so just like what we see up here, right? So the arc sine is 1 over 1 minus x squared. Then that you can see that same format here. When we try to integrate something that looks like this, then we get, of course, the antiderivative being arc sine. Okay. And so then naturally, if you can imagine, if you make this negative, it's arc cosine, right? Right. So you can see how that would work. The second one on here is the arctan, and the form there is going to be 1 over a squared plus u squared. And that's going to be the arc tangent of u over a. It's actually 1 divided by a up front too. Okay. And then the last one here is going to be the arc secant. So 1 divided by u times the square root of u squared minus a squared. Okay, when you have an integrand like that, it fits that form, use a differentiable function, a is a positive real number. Then the antiderivative here would be 1 over a times the arc secant of the absolute value of u over a. Okay. And so the arc cosecant would just be this same form, but just negative. The arc cotangent would be the same form except negative, and the arc cosine would be this same form except like a negative. Okay, and so that's basically that's the long and short of the inverse trig function. Of course, there's lots of things we could talk about with them, but I think what we'll focus on in this section is kind of like, how do you use these? Like, let's do some a few examples at least with each of these, and see sort of what the different techniques for integrating using this theorem happens to look like. So, straightforward example to begin with, just to make sure that we're all level set. Let's integrate 1 divided by the square root of 4 minus x squared. Right? If you have an integral that looks like this, well, you can look at this and say, well, this is just the integral of 1 over 2 squared minus x squared. So if I let u equal x and a equal 2, then du is dx, and I can make all my substitutions, and I'd have the exact form for the arc sine, right? Basically a squared minus u squared here. Right, so let's go ahead and do that. So this would be 1 divided by a squared minus u squared du, and then we know that that's going to be the arc sine of u over a plus c. And so we know, of course, that u is x, a is 2, so this is the arc sine of x over 2 plus c. Okay, so there's our first example. So you can see kind of a straightforward, most of these are actually relatively straightforward. Of course, there's going to be like a lot of algebra tricks that can be used to coerce the integrand into one of these formats, and we'll go through some of those in this section. But once it's in that form, then it's very much a straightforward exercise of just plugging in arc sine as the antiderivative, and kind of dropping in your u's and a's wherever they happen to be. So the trick is just kind of taking the integrand and kind of putting it into the right form, or confirming that it's already in the right form, I guess that's the case, recognizing it. So let's do some more examples here. What about the integral of 1 divided by 2 plus 9x squared? Something like that. Well, you can see that this is 1 over square root of 2 squared plus 3x squared. Okay, just kind of by looking at that, you can see you've got an a squared and a u squared. So if I let a equal the square root of 2, positive real number, no problem, and u equal 3x, then du is equal to 3 dx. Okay, then I can make my substitutions. I just have to make a small change to the integrand to multiply and divide by 3, but then I'm in good shape. So it'd be 1/3 times the integral of 3 dx over square root of 2 squared plus 3x squared. Okay, when it looks like that, then it's 1/3, and the 3 dx is du. The square root of 2 is a, and the 3x is u. Okay, and so we can see that this is going to be the a squared plus u squared, so this is the arc tangent. So this will have the form of 1/3 times, now it'll be 1 over a times the arc tangent of u over a. Okay, and so this a is square root of 2, so this will be 1 over 3 times the square root of 2. Wait a second. Nope, that's right. 1 over 3 times the square root of 2 times the arc tangent of 3x over the square root of 2 plus c. Okay. All right. Very good. Okay. And let's see. How about try another one here? Let's integrate the integral of 1 divided by x times the square root of 4x squared minus 9. Okay, so something like that. Now in this case, you'll have to notice, you can kind of see this, probably you got it queued up and you're looking at it, you're looking for it. This is obviously 2x squared there, and then minus 3 squared, right? Okay, so you've got that. So you can see that u being 2x would be a good choice, and then of course a equals 3 is a good choice, right? So if we do that, so we'll let u equal 2x, then du equals 2 times dx, okay, and let a equal 3. Okay, then we're good. So we can rewrite this ever so slightly. We'll put a 2 in the top and a 2 in the bottom. Right, so we multiply and divide by 2, and this will be 2x squared minus 3 squared, the square root of that. And then we'll just jump a line here, and we can do all of our substitutions. So the 2x is a u down here, and then I got u squared minus a squared in there, and then the 2 dx is du. So the integral of, I'll just put a du in the top, and then I've got u, and then u squared minus a squared, just like so. Okay, and this is going to match the form of the arc secant. Okay, so this is the arc secant. So this integral will look like 1 over a times the arc secant of absolute value of u over a. Okay, so it's going to have that form. So now we just come through and plug in what we have identified as u and a here, right? So a is 3, so it'll be 1/3 times the arc secant of the absolute value of u, so that's the absolute value of 2x, divided by 3 plus c. Okay, so we've got that. Very good. All right, good. So how about this one? What about this one? This is the integral of 1 over e to the 2x minus 1. Okay, so about that one. Well, something to notice here is that this is the integral of 1 divided by e to the x squared minus 1 squared. Right, so if u is e to the x, then this will be a u squared minus a squared. Okay, and so what we don't have here is, so the form we're kind of trying to match this up to would be the arc secant, because we know that 1 over u times the square root of u squared minus a squared is equal to the arc secant. I'll just put the secant inverse there. You know, this is the form we're trying to find here. So let's mess around with this for a second, though. Let's see what we have. So let's just say that u is equal to e to the x. Then du is equal to e to the x dx, right? Because the derivative of e to the x is just e to the x. And so that means that dx would be equal to du divided by e to the x. Okay. So we've got this is our u squared minus a squared, but then this dx is actually equal to du over e to the x, which of course is du over u. So that's how we get our second u here. Okay, and so we can write this as let's try to substitute it in all, very nicely. So it'll be dx would be kind of the numerator, so I'm going to put du over u in the numerator. And then underneath I've got the square root of u squared minus a squared. All right, so I have this, and of course the algebra here, we can quickly make this into 1 over u times the square root of u squared minus a squared du, right? So that's the form, perfect, right? We kind of got this other u here in a roundabout way by finding it when we differentiated u, our u as a function of x. When we differentiate that with respect to x, we get e to the x dx. So like the exponential function is kind of unique in that respect. So when we see the form like this, then we know that this is the arc secant, and so we're going to end up with 1 over a times the arc secant of the absolute value of u over a plus c. And just plugging everything in, then we get, we didn't even define our a is 1, right? So we knew that a is 1. Okay, so you get 1 over 1, so that's just 1. Leave it alone, leave it off. U is e to the x, absolute value of e to the x, and then a is 1. Now e to the x is always positive, right, for any real number, and so that means this is just arc secant of e to the x plus c. Okay, so we get that. So that's kind of a little bit of a tricky one, right? A little bit of a tricky one there. Right, so this is the thing, like maybe it would have taken a second for you to kind of choose a u. Well, you would have naturally probably began with u equal e to the 2x, then you would realize, oh wait, that's e to the x squared, so let u equals e to the x. And then you maybe would have looked at the form and said, oh, well, there's no u in the front, so shoot, what do I do? But had you just taken that one additional step, you'd see, oh yeah, the dx will be du over u, and that's where that second u will come from. So one of those tricky kind of integrals that just, you kind of got to trial and error your way through some of these. How about this one? The integral of x plus 2 over 4 minus x squared. Okay, so this guy right here. So one of the things that you'll find as you work through more and more integration is that whenever, not all the time, but very often when you see something with multiple terms in the numerator and a common denominator like this, it's very often beneficial to break the numerator apart. And so in this case, that's what we're going to want to do. So we'll write this as x over the square root of 4 minus x squared plus 2 over the square root of 4 minus x squared. Okay, so looking at this, you can see that, so kind of taking them separately. This first one, you've got this x up here, and there's not much we can do about that, but the denominator looks like an a squared minus u squared form. So if I let u equal x, then I should be able to get this guy here with just a u substitution, actually. No, if I let u equal 4 minus x squared, actually, then the derivative of u would be negative 2x. So I can I can multiply and divide by negative 2 in this one and do a regular u substitution. Okay. So we'll try that anyways, right? So a lot of the times you kind of like look at something and get an idea and see if it'll work. And then over here, this one looks like it's a trig, inverse trig, right? So this is a squared minus u squared. That's just a constant, so this would be an inverse trig integral, right? So let's do this. Let's just do it one at a time here. Actually, we'll just start with this first one. So x times, I'm going to bring this to the top, 4 minus x squared to the negative 1/2 power dx. Okay, so kind of that one's there, and then this other one is going to, plus This will be the integral. I'll bring the 2 out, and so that'll be 1 over 2 squared minus x squared square root dx. Right, and so here you can see that if I let u be the 4 minus x squared, then I'm going to get negative 2x is dx. Right, and so let's do all the substitutions here. U equals 4 minus x squared, du equals negative 2x dx. Right, so to get to do the substitution, right, I'm going to really need another negative 2 out front, so I can easily do that. I can just multiply and divide by negative 2. Over here, I'm good. U over here is going to be equal to x, and a over here is going to be equal to 2. All right, so those are going to plug in nicely. And so let's see if we can do this here. So for this first one, we're going to go 1 over negative 2 times the integral of negative 2x times 4 minus x squared to the negative 1/2 power dx. Okay. Plus 2 times the integral of 1 over a squared minus u squared du. Okay, now I'll have to go back through this one more time. So negative 1/2 times the integral of u to the negative 1/2 du plus 2 times the integral of, sorry, that should be a square root there. Just like so, okay? Right, now it's important to keep the u's and the a's separate here, right? These u's go with this one, right, which is this side, and these u's go over here. So, you know, sometimes I use u1 and du1, but then it still gets to be a little bit confusing. So you just have to be careful, just know what you're substituting into where. And so this one over here is easy to do. It's negative 1/2, and then we're just going to add 1 to this and divide by that same amount. So this would become u to the 1/2 over 1/2 when we integrate. And then this side, this is square root of a squared minus u squared. And so that's an arc sine. Right, the arc sine of u over a. Okay, so the whole thing is going to have kind of that format. And so then this can be cleaned up, and it'll be equal to negative u, which over here is 4 minus x squared. Right, that's a square root. And then over here we're mostly done, plus 2 arc sine of, and then u over here was x, a is 2. Perfect. There we go. So that's the final answer for that example. Right, so this is, you know, relatively involved. You have to break it apart. Notice that this is a u substitution. This is an inverse trig function. Kind of deal with them separately, right? You know, you've got your substitutions, and they're, you know, relevant to whichever integral. So keep that square, especially in the end when you go and substitute the stuff back in. You could completely be, you will be 100% wrong if you start plugging the wrong u in for the wrong u. So the notation can be kind of important here. You got to be a little bit careful. But ultimately, you get down to something like this. Okay. The next example is this one. So the integral of 1 over x squared plus x squared actually minus 4x plus 7. Okay, now so you've got this quadratic in the denominator, and this is going to be a great example to introduce this technique of where we'll use completing the square to help us transform the integrand into something that we can use. And so completing the square, so this is something that comes up usually in like college algebra. The idea here is, you know, if I have a quadratic that looks like this, x squared plus bx plus c, then I can add and subtract the same quantity from this without changing it. And so I can write x squared plus bx plus b over 2 squared minus b over 2 squared plus c, right? So I've added and subtracted this same quantity. And when I do this, then it allows me to complete the square, right, in the sense that I get x plus b over 2 squared minus b over 2 squared plus c, right? So I can get this squared term here. Okay, so let's do an example with real numbers. So let's say I have x squared plus 8x minus 20, for example. Right, similar to what I have here, just a quadratic. And so what I can do is, noticing that b is the coefficient on the first degree term here, that's 8. What I can do is I can add and subtract 8 over 2 squared, like so, without changing the value of the expression. And when I do that, I get, well, this is going to be x squared plus 8x. And so this is 8 divided by 2, which is 4 squared is 16. So it's basically plus 16 minus 16. All right. And so when I do that, this part here is a square, right? And specifically, it's x plus 4 squared. Right, and then this part over here is minus 36, so this would be minus 6 squared. Okay, and so using this, completing the square technique, is useful because you can think of this as your a squared minus, your u squared minus a squared, right? This could be your u, this could be your a, and so when you have something like this where you have a quadratic in the denominator, you might be able to complete the square to identify, to change the integrand to allow you to use an inverse trig antiderivative. So let's do that example. Let's do this example. So we want to integrate dx over x squared minus 4x plus 7. Okay, so the denominator can be expressed as the sum of two squares by doing this completing the square business. So let's say we have x squared minus 4x plus 7. Okay, so I can add and subtract negative 4 over 2. Okay, so it'll be x squared minus 4x plus negative 4 over 2 squared minus negative 4 over 2 squared, and then plus 7. And so when I do that, I get x squared minus 4x, and this here is negative 4 over 2 would be, of course, negative 2 squared would be plus 4, and then this would be minus 4 plus 7, right? And so when I do that, I get this guy here, which can be written as x, x minus 2, because it'd be minus 2 times, x minus 2 squared, right? So that's this part. And then this guy over here, minus 4 plus 7, of course, is just plus 3. So this would be plus the square root of 3 squared, right? That's this part. Okay, and so that means this integral can be rewritten as x minus 2 quantity squared plus the square root of 3 squared. Okay, and then when it's in that format, this is your u, right? And your du, of course, is just dx, right? So that's good. This is your a, and so this is going to be u squared plus a squared, which is the arctangent, right? And so this could be written as 1 divided by the square root of 3 times the arctangent of, and then it's just u over a, so it'd be x minus 2 divided by the square root of 3. Okay, right, so this is when you integrate this function here, this is what you get. This is the form of the solution there. All right, so that's that one. Okay, so obviously we've done a lot of examples here so far, and there's a couple things to notice here. Integration is, as I think I might have said this already, it's a little bit more like an art than a science at times. It can feel like that, like trial and error, that kind of thing can, so sometimes these integrals are easily doable, sometimes they require a tremendous amount of effort, sometimes they're doable in multiple ways. So there's, it's not quite like differentiation where it's just sort of, hey, it's got a certain form, just do it, right? It just kind of goes from end to end. It's more just, deterministic. There's not so much guesswork in the middle. But I wanted to do a couple of examples where you've got basically three integrals that are totally different, but they look relatively similar, right? So this first example, I'm going to write three integrals out here. So the first one is this, dx over x times the square root of x squared minus 1. Okay, that's the first one. Okay, so you've got that one. And then the second one, pretty similar, seemingly. You've got x dx in the top, and then in the bottom you've got just your x squared minus 1. Okay, similar. I mean, the x is in a different place, but then kind of similar otherwise. And then the third one is the easiest of the three of them. So you've just got your dx up top, and then your x squared minus 1 in the bottom. Okay, now let's talk. These all kind of look similar. So these all look they all look similar, but and I'll just write dot dot dot, right? So let's take them one by one. So the first one, right, this one right here, you basically, this is the arc secant, right? You've got a u times the square root of u squared minus a squared, right? So the integral of dx over x times the square root of x squared minus 1, that's just arc secant, the absolute value of x. Okay. This uses the arc secant rule. Kind of looks like tool, but rule. Okay, so there's that one. What about the second one? Okay, this guy here. So this is one kind of like we did a few examples ago, where basically if you take this guy here and you put it in the numerator and you express it as x squared minus 1 quantity raised to the negative 1/2 power, then this is a u substitution, right? So this one can be done as follows, right? This one can be completed really quickly. So you could write it like this. Okay, and so that's going to be 1/2 times the integral of 2x x squared minus 1 negative 1/2 dx. And ultimately, just one more step, maybe two more steps, and you'd see that this is x squared minus 1 plus c, right? Right, so this one uses a u substitution. Okay, so what we call like a change of variable, regular old u substitution, kind of chain rule style. Okay. And now what about number 3? What about this one up here? Well, this one's seemingly the easiest of all of them, but this integral actually cannot be found using present level techniques. So this one cannot be completed, right? So even though these all look really similar, right, the presence of the x and where the x happens to be makes a huge difference in what the antiderivative would be, right? So you've got in one case arc secant of x, another case x squared minus 1 quantity square root of that, and then the third case you can't even do it. Okay, so just kind of interesting to take seemingly very similar expressions and attempt to integrate them, and just seeing how different they can be. Here's another example kind of along those lines of three integrals. So the first one is dx over x times the natural log of x. The second one is the integral of natural log of x over x, like so. And then the third one is the integral of natural log of x. Okay, so the first one, what happens there? Well, this is going to fit the log rule. So this one fits the log rule. All right, so here basically the log rule, what does it say? Integral of 1 over u du is equal to the natural log of the absolute value of u. Okay, so in this case, we want to let u equal the natural log of x. Then du is equal to 1 over x dx. Okay, and so that's how you get the setup here. So the integral of dx over x ln x, that's equal to the integral of 1 over x. Well, so you can take this x down here and pull it up into the upstairs. Let's just do that. All right, kind of write it like that. That's okay. And so then this would be the integral of 1 over u du. So it's the natural log of the absolute value of u, which is the natural log of the absolute value of the natural log of x plus c, right? So there you go. That's not the prettiest thing in the world. I think we actually did this example in the previous section. Maybe in the previous section, yeah. So that's that one. What about the second example? This is going to be this. In this example, we can use a u substitution, right? So we can let u equal the natural log of x. Okay, then du equals 1 over x dx. Right, and then it's straightforward. So the integral of the natural log of x over x dx is equal to basically the integral of just u to the first power du. Right, and so when you do this, you would get u squared over 2 plus c. So ultimately, this would be the natural log of 2 squared over 2. Right, like so. And so this one, you know, obviously very different format, right? Okay, these are a little bit different, obviously, right? You've got x ln x in the denominator. Here you've got ln x kind of split across the numerator and denominator. Now, what about this third one? The integral of ln x. Well, this integral cannot be found using present level techniques, right? This is another example of those. Right, so integral of ln x dx cannot be found using present level techniques. We just don't know of any way to do this right now. Right, so we'll have to figure out, you know, maybe as we gather more capabilities, this one will become doable. Maybe it won't. There's lots and lots of functions that aren't. They don't have sort of a closed form antiderivative that we can just plug in. Okay, so that sort of takes care of the inverse trig function side of this lecture. So next we'll jump into hyperbolic functions. I think I'm going to split the video in two, though, just to keep the time down. So we'll jump right back into this with a part B for the hyperbolic functions.